Hello, Science Lines. Hello, it's me, Lara. I am dressed as Marie Curie today because this week's show with the latest story time is about Marie Curie, which is very appropriate because she discovered radiation, and this whole lesson is on radioactive elements. It's massive. I'm so sorry. If there's any teachers watching, this is not what our training was about. It's far too much information in this lesson. I got carried away. It's the last lesson on the periodic table. Let's go. Let's waste no more time. But you don't have to remember everything I'm telling you today, okay? It's just out of interest, right? Just getting us fired up about science. All you need to know, if you haven't been to any of the previous lessons, is that atoms are positive particles called protons with teeny, tiny, like they barely have any mass, they don't have mass, electrons that are negatively charged whizzing around the outside, okay? And we've learned that positive things and positive things push away from each other, are repelled by each other, and opposites attract, right? So electrons and protons attracted to each other. And that's it. And I kept saying for the last 4 lessons, there's another particle in the middle of the atom, but we don't need to talk about it. We get to talk about it today. Ooh, that's an interesting noise. There is also, wow. New charity shop pens. Just don't do it. What do you think? Okay, there's another particle right in the middle called a neutron, which, as its name suggests, has no charge at all. It doesn't feel attracted or repelled by positive or negative things. It's a neutron. But that's what we need to concentrate today, is the proton and the neutron in the very centre, what we call the nucleus of the atom. We're not really going to worry about the electrons in the shells around the atom at all today. So don't worry if you haven't been to any previous lessons. Here's what I have told you, which you may or may not remember. The number of protons an atom has is its atomic number, all right? So this atom has 3 protons, so it must be lithium because the number of protons decides what the atom is. And if you find lithium in the periodic table, you'll see it. It's got a number 3 in one of the corners. That tells you how many protons it's got, all right? And we've looked at how atoms are arranged in the periodic table by the number of protons. Look, I mean, this is the easy bit, right? Hydrogen, it's got 1 proton, so it's there. Helium's got 2 protons, so it's the next one along. Lithium's got 3, beryllium's got 4, yeah? You get it. But proper periodic tables show, gasp, 2 numbers next to each element. So what do they mean? Well, you might know this already. If you don't, I'm just going to linger for a few seconds on a couple of examples. I think you'll be able to work it out. So here's a helium atom, a diagram of one. You've got helium here on the periodic table. It's got a 2 in the top left corner. That tells us how many protons there are, okay? 2. But there's a 4 in the top right corner. What does that mean? So it's got 2 protons and 2 neutrons in the centre, in the nucleus, and it's got 2 electrons whizzing around the outside. What do you reckon that number 4 means? Here's another example. Here's lithium. The number in the top right corner on lithium is 7. So you've got 3 protons in the middle, 4 protons in the middle, and 3 electrons around the outside. What does the 7 mean? You decide. You don't decide. It's a fact. Carbon, it's got a 12. So you've got 6 protons in the middle, 6 neutrons in the middle, and 6 electrons going around the outside. What does the 12 mean? One more example. In oxygen, it's 16. You've got 8 protons in the centre and 8 neutrons in the centre, in the nucleus of the atom, and then 8 electrons whizzing around the outside. Okay? Right. Well, some of you, if you're saying, well, it's too easy, Lara, well done if you worked it out. This number in the top right corner is the number of protons and neutrons all together, which is the atom's mass. Okay, so the number of protons and neutrons all together inside the centre of the atom, that's the number on the right-hand side. You can basically say it's like how much the atom weighs, because electrons don't even really count. They've got hardly any charge. Neutrons and protons, they're pretty much the same size. Neutrons are, I think, a tiny bit bigger, but we'll just say they're the same. But they do at least weigh something. Here we go. So number of protons and neutrons all together, that's what that number is, because electrons hardly have any mass. But excuse me, we've been looking at this periodic table a lot, and you may be thinking, Lara, in the top corner of lithium, it's not 7, it's 6.94. And if you look at a lot of the other elements in the periodic table, you found they've all got like, tins is 118.7. What does that mean? I'm just putting lots of question marks and exclamation marks. What? Well, what it is, we've seen before how the number of protons decides what an atom is. This has got 3 protons, so it's definitely lithium. We know that it can have a different number of electrons, and it's still lithium. You can say the same about the neutrons. Atoms can have different numbers of neutrons, and it doesn't change what atom they are. I'm just burning one of the neutrons in lithium to prove that, look, it's still lithium. So here we go. Someone asked me about this the other day. What's an isotope? Atoms with different numbers of neutrons are called isotopes. So here we've got hydrogen, the one that we're used to, just one proton with one electron whizzing around the outside. That's hydrogen. But an atom does exist like that, but it's got a neutron in the middle as well. It's called deuterium. It's in the sun. And if you add 2 neutrons, it's still hydrogen. So you would say that these are all isotopes of hydrogen. It's got a different number of protons. So this number in the corner, if it looks a bit odd, the number of protons and neutrons added up, it's because it's showing you like the average number of neutrons that an atom have. So we can see from this, if all lithium atoms had 4 neutrons, then 3 protons plus 4 neutrons would be 7. But this is telling us that some lithium atoms must not have 4 neutrons. It turns out they've actually only got 3, which is why that number is, on average, slightly less than 7. Okay, whew, stay with me, people. I'll be flipping you around soon. So we've seen how losing or gaining electrons makes some atoms more stable. Yeah, we've been talking about how atoms react in ways that makes them more stable, and they don't like having shells that aren't full. So if you get a sodium atom and a chlorine atom next to each other, then the sodium atom gives the chlorine atom an electron, and then they've both got full shells and they're both happy. Okay, makes them more stable. Well, having a wonky number of protons and neutrons can also make an atom unstable. So these hydrogen isotopes that I showed you, the first one, the one that we know, stable. The second one, deuterium, which is in the sun, also stable. The other one with the 2 neutrons, that is just not a combination of protons and neutrons that works well, so it's an unstable atom. We would say that it is radioactive. And there's some elements, some atoms in the periodic table, they don't have any stable isotopes. Like, they exist, their normal version of themselves, if you like, that exists, is all unstable. So the ones in yellow here are all the radioactive elements, the ones that are unstable, the ones that want to spew stuff out in order to get more stable. So let's craft while I explain why some atoms are unstable. I've put science craft, so it'll be 3% good, 100% learning. Yes, I know that equals 100. Shush, come up here. Okay, so what I want you to do, calling it a craft is a little bit generous. Have you got a piece of paper with you? Any piece of paper? I'm using some scrap Let Them Eat Cake notes from last week's story time. If you've got a piece of paper and a pen, just sort of scribble pen all over one of the sides of the piece of paper, okay? And then we're going to cut strips and cut across them to basically just make loads of little squares. Here's one that I made earlier. See? What you want in the end is loads of piece of paper. How big's that? Right, sort of 250p's. It doesn't matter if they're all different sizes. You just need loads of little pieces of paper that have got pen on one side and nothing on the other side. Okay, two different sides. So when you're colouring, make sure the pen goes right into the corners, yeah? Because you don't want to have any coins that have got nothing on both sides. You need pen on one side and nothing on the other side. Right, I better get, I'm supposed to be explaining stuff while you do that. So once you've done that, cut it up into little pieces. So you get what I'm holding in my hands now, all these little squares of paper, yeah? I've got pen on one side and ink on the other side, so I did it wrong, but it doesn't matter, as long as the sides are different. Okay, why are atoms unstable? This is quite a complicated question. If you look this up on like BBC Bite Size, it'll just say something like if it's got a wonky amount of protons and neutrons, like if the ratio of protons and neutrons kind of isn't right. Well, we're going to a little bit more than that while you're cutting and scribbling. I have here a pink magnetic star. I've put it on my whiteboard. The whiteboard's made of metal, right? The pink star is magnetic. I'm so snotty. It's not relevant to the question. What forces are acting on the star? The star is experiencing some forces. Can you tell me what they are? One of them you should definitely get. It's one of the forces that we're all experiencing on Earth right now. It's too much of a clue, isn't it? Yeah, so hopefully you're shouting gravity at me. It is experiencing gravity. It is. But it's also experiencing another force, isn't it? If it was only experiencing gravity and it would be falling, it's not falling. We'll say, at this level, it's like the force of magnetism is also acting on the star, okay? So it's being pulled by magnetism and it's being pulled by gravity. Which force is stronger in this case? Which force is the star feeling more? It's magnetism, isn't it? Magnetism is winning in this case. Gravity is not winning or the star would be falling. Okay? Is that all right? So you have a situation where there's two forces acting, but magnetism is stronger. We think about gravity as being a very sort of powerful force because it's everywhere. But of course it is very weak. Like every time you pick up a pen or lift your foot off the ground, you are kind of beating gravity. So inside the nucleus of the atom, the nucleus is just the bit in the middle, yeah? Like I say, we're just going to ignore those electrons whizzing around the atom today. Inside the nucleus, you've got protons and neutrons. If you've been really paying attention, you might have noticed already that there's definitely a force acting in the centre of this atom, in this nucleus. Because I keep telling you that positive things and positive things push away from each other. But look, there they are. Stuck together, the protons, they're all positive. Why aren't they pushing away from each other? Well, there is a pushing away force in there, like sort of the electric force, the force that pushes charges away from each other is definitely acting. But there's another force acting which is winning, and it's called the strong nuclear force. You do physics A level, you'll learn about strong nuclear force. It's cool. Yeah, the strong nuclear force is strong. So it's beating the force that would push the protons apart. But it doesn't work over a very long area. So once atoms start getting really big, once the nucleus starts getting really big with loads of protons and neutrons, the strong nuclear force sort of doesn't win. It's more complicated than that, because as you might have noticed in this periodic table, some of it, look, technetium up here, it's quite small and it's still radioactive. It's called technetium because humans sort of kind of came up with it, created it. There's not much of it in natural world. Anyway, yeah, it's more complicated than that, but that gives you a good idea of what's happening and why, generally speaking, it's the larger atoms that are radioactive. Right, have you done your craft? Okay, what I want you to do is put the... I've trademarked a couple of special moves today so that we can do this craft. Put them all on the table and give them a smush. Because what we're going to do eventually is sprinkle them all onto the table or sofa or carpet, wherever you are. And we want some to turn pen facing upwards and some to turn pen facing downwards. So you can't just have them in a stack and drop them because then it'll be like all pen facing up, it won't work. So give them a good smush to get them all mixed up, okay? We're calling this the smush and sprinkle. I'm going to get tote bags made that say, do you smush and sprinkle? I do. And then science alliance, when you're walking around town, you can spot each other. Okay, so I've smushed. Don't worry if you're a bit behind. Like I say, you can still be doing, there's a lot of information coming up and this is going to take me a while. I've smushed, I'm now going to sprinkle. Right. So what we're going to say, just while you're smushing and sprinkling, I'll explain. We're going to say that this collection of little bits of paper, the whole thing all together, is like a lump of radioactive material, all right? And we're going to say that each bit of pen facing upwards is an atom that has decayed. I'll explain what it means if something decays. So we've got this atom, which is unstable. To get more stable, it shoots out an alpha particle, okay? I'll show you like this. Here's a great picture of that happening. So to become more stable, some nuclei, not all of them, but some nucleuses in the middle of the atom shoot out an alpha particle. An alpha particle is 2 protons and 2 neutrons joined together. Just wait for people to catch up with the craft and I'll go through this. Yeah, so 2 protons and 2 neutrons stuck together is an alpha particle. It comes speeding out of the nucleus, which just a reminder that all the protons and neutrons together are the nucleus of the atom. We're not worried about the electrons going around the outside. And nuclei means more than one nucleus. I'm sorry, don't blame me. Blame Latin. This is called, we say that the atom has decayed, all right? When an atom decays, it's completely random, proper random, not like we decided Olivia is a vegetarian vampire last lesson, how random, like truly random. It cannot be predicted and there's nothing you can do to make the nucleus decay. We have no idea when it's going to happen. So here is plutonium-238. That means it's an atom of plutonium that's got 238 protons and neutrons. So this is obviously a collection of a lot of those atoms, right? Loads of atoms bonded together. It's a lump of plutonium. If you're thinking, that doesn't look very stable, you are correct. It's not. It contains trillions of unstable nuclei, but there's no way of saying when one of them is going to emit one of those alpha particles. But, oh, maths, you beauty! We can use statistics to work out how long it will take, on average, for half of this lump of plutonium to decay. So that's what we're doing with this activity. So what I want you to think is that each bit of paper that's got pen on it that's facing upwards, that is an atom from this lump of plutonium, or I suppose a nucleus I should say, that has decayed. So it's decayed, it's lost an alpha particle, it's not plutonium anymore, we're going to get rid of it. So take away all the bits of paper that I've got red pen on, well, whatever pen you've used. It's taking quite a long time. Okay, so I'm going to stack them all onto the side and say that after one sprinkle, that many nucleuses had decayed. And the ones that you've got left, collect all those up again. There's another one hiding. Right, phew. Okay, so that was after one sprinkle. I've got only this amount left. So do the scrunch again. Do the scrunch, do the scrunch, boom, boom, and then sprinkle again. Whew. And any ones that have got pen on them, take them away. This is good. Not as many now, it's getting a bit faster. So after 2 sprinkles, I've got this many left. Oh, what's that? Only 6, great. Do another scrunch. Do a sprinkle. Are you getting it? You can keep doing this while I explain in a sec. Oh, good. So I've only got 3 left now. And you just keep going and going until all your atoms have decayed, all right? Oh, let's call that. Now I suppose they're all still left. So after 4 sprinkles, I still had 3. They've all gone now, good. Phew. So after 4 sprinkles, my pretend lump of plutonium model had all decayed, all right? Why on earth am I doing that? Well, are you okay with the fact that which pieces of paper ended up pen facing upwards was totally random, wasn't it? It was just like flipping a coin. There was no way of predicting how many bits of paper were going to be pen upwards and how many were going to be pen downwards. It was totally random. It could have been that the first time you sprinkled it, they all were facing upwards, and maybe one time you sprinkled it, they all ended up facing downwards. But that's unlikely. So if you do that again and 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 again, eventually you'd probably have quite a good idea, wouldn't you, of how many times you had to sprinkle before all your atoms had decayed, all your nuclei had decayed. And this is what happens. You can't look at an atom of plutonium and say when it's going to spew out an alpha particle. But if you get loads and loads and loads of atoms of plutonium all together, you can say roughly how long it will take for them to decay, because it's basically just like doing that activity again and again and again and getting an average. So this is where the phrase that you might have heard of called half-life comes from. Okay, the half-life of an atom is, on average, how long it takes for half of the substance to decay. All right. So if I started out with 100 pieces of paper, how many sprinkles it took for me to get to 50 would be kind of the half-life of my bit of paper. Except instead of sprinkles, it's time. So the half-life of an atom could be thousands and thousands of years. It could take, on average, thousands of years for the atoms in a substance to decay, or it could be like split seconds. Sometimes the things hardly last any time at all. Right, I couldn't get this into my head. Why giving off an alpha particle in particular would change the ratio of protons and neutrons in an atom? I just can't picture it, because it's 2 protons and 2 neutrons. So how does just giving out the same amount of protons and neutrons make an atom more stable, affect the balance of protons and neutrons? So I did a thing to show you, just in case you were as confused as me. I'm still not sure I really understand this, to be perfectly honest with you. I will try and explain, though, using maths. Here we are. This is Lara teaching maths. Let's say we've got a nucleus which has 6 protons and 18 neutrons, okay? I'm just going to put them in lines to make it easier to understand. But this is what's happening inside the nucleus of an atom. This is not a real example. I'm just keeping the numbers small so that we have an idea of what happens, okay? Can you see that the ratio of protons to neutrons in this case is 1 proton for every 3 neutrons, all right? That's just what a ratio is. Here we go. So I've split them up so you can really clearly see, yeah? For every 1 proton, there are 3 neutrons. Fine. So let's say that this atom loses an alpha particle, okay? The 2 protons and the 2 neutrons stuck together. Look what's happened to the ratio of protons to neutrons. Honestly, I can't get my head around this. But suddenly we've lost the same amount of protons and neutrons, but now there's 1 proton for every 4 neutrons. So the ratio in our nucleus has completely changed, which indeed could make it more stable. Let's have a look at a real life example, okay? Here's the bottom of the periodic table where the fun happens. Let's have a look at americium. Americium has, it's called americium 241 because it's got 95 protons and 146 neutrons, okay? If you add them together, you get 241. It's not very stable. I haven't bothered to draw them all, but it gives off an alpha particle, right? You ready? Pew! What element is it now? Some people on Facebook got this straight away and some people were struggling. You've got an atom, it's americium, and it's got 95 protons in it and 146 neutrons. If it gives off an alpha particle, like it just loses 2 neutrons and 2 protons, what element is it? Is it uranium? That's got 92 protons. Is it neptunium? That's got 93. Is it plutonium, which has got 94? Curium? There she is. Named after Marie Curie, obviously, who Lego Storytime is about today. It's... well done if you said it was neptunium. Yes, because it's lost 2 protons, and it's the protons that tell us what an atom is. So americium has 95 protons. If it loses 2, then it's neptunium. So it's kind of cool and weird. It's like once a radioactive element has decayed, then it sometimes means that it's not that same element anymore. Now, I'll just tell you this. We haven't really got time to go into it, but radiation can be extremely dangerous. It can also save lives. So americium is a good example. It's used in smoke detectors. Other radioactive elements are used to date fossils, work robots on Mars. I've said we'll do a whole series of lessons on it at some point. I haven't got time to tell you now what's good and bad about radiation. We really should. I mean, we could just do 6 lessons on radioactivity easily, which I think we will. But anyway, let's move on. Tennessine, there it is. To give you an example of a sort of man-created, human-created element, we made it in 2010. We made it by smashing together calcium, our old friend, and berkelium in one of these. Isn't it beautiful? This is a particle accelerator. This is actually Fermilab in America, but you might have heard of CERN, which is in Europe, like France and Switzerland. Yeah, they're just enormous kind of donuts under the ground, which accelerate particles to tremendous speeds using magnets and then smash them together. So how, was it americium? No, how tennessine was made is that those 2 particles got smashed together, and for a very brief amount of time, 117 protons were stuck together. It was like, we've got tennessine. Oh, it's gone. Because a lot of this is why new elements keep getting added to the periodic table, because humans keep not inventing, but creating more of them with sort of better technology. But they only last a tiny amount of time because they're so unstable that they very quickly just decay into something else. That is where I wish I'd ended the lesson, in all honesty. But I've got a tiny bit more because there are other kinds of radiation, and I just want to quickly tell you about the other kind, give you a little puzzle, and then it's the end. So there are other types of radiation. For example, carbon-14 has got 6 protons, obviously, or it wouldn't be carbon. And it's also got 8 neutrons. But carbon-14 can do some kind of radioactive decay thing to make it turn into an atom of nitrogen. What's happening there is my puzzle for you. It can't be alpha decay, can it? If something with 6 protons is becoming something with 7 protons, what is happening? I wonder if you can tell me. So how does something with 6 protons and 8 neutrons, yeah, carbon-14, got it on the board here. How does that turn into this with 7 protons and 7 neutrons? It's not anything to do with, you know, you don't have to prod it or poke it, you don't have to burn it. It's just sitting there and something just happens. What happens? It's actually sort of weirdly simple, but I don't think I would have got it. This arrangement, 6 protons and 8 neutrons, is an unstable arrangement. To get a more stable arrangement, one of the neutrons decays into a proton. Neutron turns into a proton, people. Look, can you see? If a neutron turns into a proton, then there's the same amount of protons and neutrons altogether, but we've got 1 extra proton. Genius! Except this cannot happen. This is breaking the laws of physics. Honestly, it can't happen. A proton has got a charge of 0. It can't just turn into something that has a positive charge. That is against very fundamental laws of physics. Charge has to be conserved. Like, you can't get something that has no charge just turning into something that has a charge. But what you can get is something that has no charge decaying into something that's positive and something that's negative. That's fine, because like the positive and negative thing add up to be neutral. So that's fine. So that is in fact what happens. A neutron turns into a proton and released from the very centre of the atom, from the nucleus. You ready for this special effect? Whee! You get an electron! I've done it in yellow to try and show you that it's not an electron from the outer shell of the atom. People at GCSE get this wrong all the time. It's just created inside the nucleus when a neutron turns into a proton. They also release an electron. How good is that? Okay, whew, right, that is actually the end. I just want to tell you a little story now, because a lot of you, when you thought about radioactivity, might have thought of uranium. Because uranium-235 is used in nuclear power stations. Nuclear power stations can be brilliant. They produce a lot of energy which doesn't release any carbon dioxide into the atmosphere. So using nuclear energy to make electricity doesn't sort of, cause global warming or any of this bad stuff. But this is a picture of a very famous nuclear power station at a place called Chernobyl. That's the reason why the photographer is so far away. So there was a horrific disaster at the Chernobyl power station under the command of the Soviet Union. It was Russia that were in charge of it. And basically it was just very, very, very poor management, poor staff training. A lot of things went wrong. And the top blew off. And a lot of radioactive material, fuel, went just spewing into the atmosphere. I'll given you a list of some of the most dangerous materials that went into the atmosphere. There was iodine, strontium, and cesium, which we've looked at, you know, the one that if you put in water, it gets very excited. So iodine's got a half-life of 8 days, strontium's got a half-life of 29 years, and cesium's got a half-life of 30 years. All three of these atoms emit extremely dangerous radiation that damages human cells. So everyone had to evacuate. Here's some photos of what Chernobyl looks like now, because there's just no one has lived there for 40 years. So nature is just taking over. Isn't it amazing? This is a ship that has been in the water for 40 years and is starting to suffer. So when will it be safe for people to return to Chernobyl then, do you think? Is it after 8 days, after 29 years, after 30 years, after 60 years, thousands of years, or never? People can never go back to Chernobyl. I'll give you 5 seconds. So some people were saying in the last lesson that it would be after 60 years, which was a very good shout, because cesium has the longest half-life, right, of 30 years. So you might think, well, then after 60 years, all of the cesium will have decayed and won't be radioactive anymore, so you can go back. But no, the answer is actually thousands of years. Because when something that is radioactive decays, it might still decay into something that is still radioactive. And then even that might decay into something that is still radioactive. And of course, like a half-life is just an average. So yeah, it's going to be literally thousands of years before people can return to Chernobyl. I've put in my Facebook group some links actually to, there's a Ben Fogel documentary, which a lot of people are recommending. I haven't seen it, so I can't say hand on heart that I think it's suitable for children, but like most of the Science Alliance adults are agreeing that it's totally awesome, you should watch it. Yeah, I've linked to a little video from one of my favourite teachers about a bit more about how that model of the sprinkling and scrunching works, except he's using dice. Boring. Okay, that is all the information that I needed to give you about radioactivity. I have 4 past paper GCSE questions for you, or like loosely based on, which are mainly multiple choice, which I thought you could have a go at. You don't have to have listened to or understood the entire lesson to be able to do these questions. I'll be interested to see how you get on. Before I do that, I should tell you a few things. This was our last lesson on the periodic table. It's been such a good one. I've learned so much. So I'm taking a week's break for half term because my kids are off school and that just wouldn't work. And then the week after, we're going to start a biology topic. We're going to do ecosystems and food chains for, I think it's 5 or 6 weeks. And then after that, I think we'll do some physics. Yes, if you are enjoying these lessons, and you want to support me, you totally can. In fact, I absolutely could not do this without people supporting me. So it's very much appreciated. If you go to my About section on YouTube and you go to the website called Coffee, you can support me with £5 or £6 a month. I go through phases where I'm really embarrassed to say it, and I go through phases where I'm like, that's amazing value. This is such a good business model. £5 or £6 a month. And I can do IGCSE physics lessons for free, and these lessons for free, sort of all ages home ed, and the show with the Lego story time. And I'll send you the Science magazine every time I've written it. The next one is on sleep. I'm going to be using half term to quickly finish off. But yeah, if you sign up now, I'll send you this. It's my favourite one. It is it's one of my favourite ones. I love them all. This one's on colour. It's a bumper issue. It's got a comic about Monet in it, the French painter, and how he had a superpower that he didn't like. It's got ideas for activities. It's got an article about how the primary colours of paint are just not what you think. It's got some optical illusions in it. I'm very proud of the Science magazine. Thank you to everyone who's getting it. And I'll also send you some rainbow glasses because he doesn't want rainbow glasses. They're super cool. Okay, here's your past paper GCSE questions. What particles are found in the nucleus of an atom? Is it electrons and protons, neutrons and electrons, protons and neutrons, or protons, neutrons and electrons? Question 2. The diagram shows a helium atom. Which part of the atom is the same as an alpha particle? So we've got a diagram of a helium atom. Is the alpha particle the same as A, the neutron, A, the proton, B, the neutron, C, the shell that the electrons are in, D, one of the electrons, or E, the whole centre of the atom, the protons and the neutrons together? Number 3, this was catching people out last time. What can you do to change how fast a radioactive substance decays? What can you do to change how quickly, say, an alpha particle is given off? Nothing, freeze it, boil it, keep it in a jar of oil, or keep it in a box lined with lead. And number 4, during beta decay, an electron is given off. Where does the electron come from? Is it the outer shell of the atom, the inner shell of the atom, or the nucleus? Goodness me, that was such a lot. Such a lot. I'm going to go blow my nose very quickly and then tell you the answer. Oh my goodness, I can't believe how many of my nose blows are like captured on YouTube forever. Right, let's go through the answers. The particles inside the nucleus of an atom are protons and neutrons. Protons and neutrons. If it was a proton, neutron and electrons, that would be the whole atom, but we're just looking at the nucleus, the middle. In this diagram of a helium atom, it's E. Yes, alpha particles are exactly the same as helium nuclei. Someone was asking me about this the other day. Why don't you call it a helium nucleus? I think the answer to that is they discovered alpha particles long before they discovered what they named alpha particles before they discovered what they actually were. So they knew that something was coming out and they called it an alpha particle, but it was quite a long time later that we found out that it was 2 protons and 2 neutrons stuck together. What can you do to change how fast a radioactive substance decays? Nothing. It can't do anything. It's totally random. It is the genuine definition of random. It can't be predicted. During beta decay, an electron, I've told you this so fast, but that's the situation where the neutron decays into a proton. So the answer is, oops, the nucleus. It's a common mistake GCSE students make to think that it's one of the shell's electrons that whizzes off, but it's not. The electron comes from the inside. Okay, I'm just going to go, before we go to my Facebook page, because I put up my usual post on there saying, I'm teaching a lesson on YouTube. If you're watching live and you want to say hello, then please say hello. So I'll do that now. You got those answers, right? Yeah, so I'll just go to my Facebook page and see if anyone's got any questions, because there have been some excellent questions about radioactivity during these lessons. Go to my Facebook page. It's always a bit awkward, this bit, isn't it? Just watching me. Ooh, there's a lot of comments. That means people have got good questions. Oh, it's Bella. Would you consider teaching us about marine biology? What? That would be so cool. Oh yeah, we should definitely learn about marine biology. Oh, yeah, that's a great idea. Is that Bella loving all my clothes again? Yeah, this one's good. This is one of the things that I got new from, I can't remember. Wait, I'll answer that question later. Chernobyl is just so sad. Oh, maybe it was the Ben Fogle thing that you watched. Yeah, it's unbelievably sad. Oh, Zaki can't find me. Hopefully he found it. Yeah, he got there in the end. Well done, Zaki. Hello. Just to say that today you are not glitchy. I know, just whisper it. The glitches seem to have stopped. Occasionally I'm getting a little wheel and it freezes for like a second. Oh, hello, Laurie. You're having a proper science day today. That was a good nose blow. Oh, don't be gross. Ah, amazing, look. Oh, I never get pictures. I've got a proper picture of Bella because you got the GCSE questions right. A neutron decays into a proton. I know. A-level physics is so fun. It is very cool. Okay, that's nice. All right, you're not? Brilliant. Okay, shall I tell you where my top's from? And then everyone else can go. Where is it? Does it say it on here? Yeah, here it is. Oh, it's from Thought. Yeah, it's from this website called Thought, which is all very designed in London consciously. I thought it said conscientiously. It just says consciously crafted in China. Thought, do you mean made? Anyway, apparently they're quite eco-friendly and it is super cool. And last time I looked, it was in sale, which is where I got it from. Bella and fam, go to the Thought website and see if it's in sale. And you too can dress like Marie Curie. All right, I'm gonna go. If you haven't seen the show on Marie Curie yet, it is on YouTube at 2, which is where you are, at 2 o'clock today. So very soon. So have a nice rest of the day and I might see you there. If not, don't forget, don't come to anything that I do next week because I won't be doing it because it's half term. But the week after, it's all back to normal. Except there's no Marie Curie show on the Monday morning because I can't leave Lego Storytime in my house for 10 days because my children will just destroy it. So only 2 Lego shows this week and then on a Monday. Okay, right, I'm going to go. Thanks for coming in.